In photoelectric effect, we use the photoelectric effect to explain the particle nature of the waves. Similarly, to explain the wave nature of particle, we have an experiment, that is the Davison-Germer experiment. As per your new syllabus, there is no need of studying the entire background of the experiment. Just you should know what is the result and what was the purpose of the experiment. So the purpose of the experiment was to show the wave nature of electron. The Davison-Germer experiment was performed to show that the electrons are behaving like a wave. So the entire experimental setup I am going to show you. This is the experimental setup for verifying wave nature of electron, that is the Davison-Germer experiment. Here you can see a LT is there. LT is actually means low tension. It is actually giving the, it is connected to a filament which provides the electrons like this, and this high tension circuit is for giving a potential here for accelerating the electron. So this accelerated electron is going like this. So the electron is going through this way and it is hitting the nickel here. Nickel target is there, and from here it is deviated and it is going here. So here we have a galvanometer with a movable collector and all. Just this setup is to measure how much electrons are coming in different directions, and this angle is measured, and we can move like this, and in each angle how much electrons are coming, that can be measured using this experimental setup. So this entire thing is in a vacuum chamber because the electron should not hit with any other gas molecules or something. So this can be varied, that is the accelerating potential can be varied, and we can measure it for different angles. So this is the experiment done, and we got the highest intensity at an angle of 50 degree at a potential of 54 volts. In this experimental setup, what they used is they use a particular crystal. So in that one, they made the electrons to hit there, and the electrons are scattered in different directions. When the electrons are scattered in different direction, in each direction they collected how much electron is coming. So that is the intensity of the electron they collected. So when they done this experiment, what they understood is these electrons which is moving in a particular direction, that is at an angle of 50 degree, and when it is accelerated with a voltage of 54 volt was maximum. That is at 54 volt accelerated electron is moving in an angle of 50 degree is maximum in that one. So if you compare this one with the diffraction, that is you have two layers of the crystal, so the one wave is coming and it is hitting the other layer and is undergoing diffraction. So if you compare with that one, this here we can see if the electron is behaving like a wave, we can calculate using the previous equation. We can calculate what is the wavelength of the electron, and for this particular crystal we can calculate if it should show the diffraction, what should be the value of wave required. So when we compare these two, we can say these two wavelengths are coming very close, or it's almost same. So the meaning of that one is, in Davison-Germer experiment, we used the electron and we got a maximum intensity at 54 volt and 50 degree. That is because the electron behaved like a wave there. So finally we can say electron behaves like a wave in the Davison-Germer experiment, and this wave nature we are making use of it. In the case of electron microscope, we are making use of our wave nature of electrons.